A warm welcome to another session with data with Nick the Greek. So today's topic is Spark partitions. We will not use data loaded yet from a file store, but really generate some data frames and observe what are some of the influence factors who influence the number of partitions. And also have a short look already what are the performance influence of Spark partitions. So let's get started. I already executed my Spark session. What's gonna be important today is that I have, basically a single node cluster with 4 cores used. And as we're talking partitions, this is gonna be, as you might already guess, one of the influence factors we're gonna discover a little bit more in detail today. So let's have a look on the data first of all. So I generated 2 functions generating data. So one is based on our dictionary we had from the last episode. So what I'm just doing here, depending on the variable number iterator, I just extend the list of dictionaries and generate a data frame out of it. Not the most efficient approach, but I use it to generate a little bit more Spark data frames using Spark create data frame, and how our data frame looks like we can see here. So if you execute it with 2, we have 10 dictionaries. In every case, we're gonna get 20 rows, and we can also see here the data frame in a second. Okay, I'm surprised it's a bit slow that time, so we can see exactly the 20 rows just duplicated. We also have a second data frame generator using the Spark range. The good thing is about you can not only define the number of rows, but you can also define the number of partitions. And I generated some additional columns like a date, like a timestamp, and 3 strings, which are actually numbers, just to play around with the data a little bit later on. So also when we are executing this here, you see it's way faster as we don't have this dictionary append topping in the background. We can also see here the data. We have the ID, today, timestamp, ID string, and ID last. So let's start with the partitions. So first of all, the most important thing is to understand what's the default parallelism. So there's a variable in the Spark context, default parallelism, which basically returns you the number of cores. And you hopefully remember out of the architecture, the number of cores is the maximum number of tasks you can execute. And each partition is executed as one single task on one of those cores. So there's already a connection, and there are multiple ways how you can find out how many cores you have available. So this is the one option. We already guessed it here as mentioned. We generated a cluster with 4 cores, and also if we're gonna run now a data frame, you're gonna see that the number of partitions which we have here is actually 4. Another option is also to go to the Spark UI under executors, and like in this case we only have one executor with 4 cores. If you have a multi-node cluster, so with multiple workers, you're gonna see that the core is gonna be 0. Then if you have 2 workers, you're gonna have 4 instances. If you have this similar setup, 2 times 4 cores, and then here the summary gives you like the sum of the cores, which is 4 in this case. So now what we can do is to just visualize a little bit how the partition IDs. So we already saw that we have 4 partitions, and we could use with column partition ID to basically represent and show the partition ID which we have for each row. So we have 20 data points, and then you already guessed it, 5, 5, 5. it already distributes the data quite uniformly. And if you're looking here on an aggregated view, we can see, okay, per partition ID, we're gonna have 5. Let's wait a second. So we have 20 data points, and we have uniformly with 5 data points per partition data available. And if you're gonna run a job for that, we can also do it. It's gonna take a few seconds. We can already jump to the Spark UI. Under jobs, we see the same behavior. So this is our experiment which we just executed, that we have, as you already learned, one stage for a narrow transformation and 4 total tasks. And if we jump, that's where we're gonna jump today quite more often. If you go to our details for the stage and to the event timeline, we see that we have quite uniformly, well, one is a little bit longer, but quite uniformly execution time. So you can also see here the statistics that we have like 4 completed tasks, and the minimum 25%, median 27th percentile, and the max is around about 6 seconds for the execution time. And here you can also see the details for each task. Let's repeat this experiment for a little bit bigger data frame. So we show data frame, we do a count. So in this case, it should be 2,000. No, 20,000, because each dictionary has 10 records. And then also when we do the statistics, it should be roughly uniformly again. So here we have some slight deviation. Yeah, Spark sometimes it's doing it, but it's not too bad. It's not a big variation of having like 4 equally sized data sets. And if we execute our job again, didn't take longer. We're gonna go to stages this time straight away. The first generator, experiment 2. We can see again quite uniformly, okay, one took this time a little bit longer, as you can see, and we can also sort, and this might be most probably the one which had a little bit more data, but it's still not a high deviation. You're gonna see more complex executions that we can see significant more deviations in time for each task. So that's actually still acceptable, but I guess you already saw the point that like for narrow transformation, the most efficient way is to have your partitions as equally sized as possible, as uniformly, so that all cores are working with the same capacity. Meaning you don't want that one core is just standing around doing nothing and then another core is basically doing everything. We're gonna see it also when we're gonna play a little bit with the other partitions, meaning they're gonna be like 2 rules. Try to have a uniform distribution across partitions and also have a number of partitions which is equivalent or divisible by the number of cores you have. So if you have 8 partitions, you're gonna have like 2 iterations, 2 executions per core, and if it's additionally uniformly, the execution time for all those partitions is gonna be also similar. One thing which I'm not showing now, but also want to mention and note it here is, of course, we can increase this now more and more, but the size of the data doesn't really have an influence on the number of partitions. You already saw it here. If you're loading files, you're gonna see later that there is some influence factors, but in this case, it's rather ends up that your processing gonna take just too long, or you reach some out of memory or in the worst case even out of disk errors if you generate like really huge dictionaries in memory and then make a data frame out of it to save them. So that's like important to know that in this case, you might want to increase your cluster setup to have like more cores, for instance, or save the data in smaller batches, so that you do the Spark execution based on this on your save files. Now we are repeating the same experiment, just with the other generator which we created. So in this case, we have, let me count, 2 million of rows which are defined. Again, we see 4 partitions. And then we can see the data, the partition ID has been added. If we do the count, we can see that we have 2 million data points. And if we aggregate it as before, we see that it's perfectly distributed with the 50,000 count. And if you're running our job again, we're gonna go to stages. Now we have the second generator. Experiment 1, we see again we have 4 tasks as expected. And now I'm not sure why it didn't do for create data frame. It even shows us here per task how many rows have been executed. So we can see this distribution of time again. We have some garbage collection and scheduler delay here. It's also like a little bit more data as we had before. That's normal, but in some cases you should also observe if your scheduler GC time, garbage collection time, becomes like really actually it's task deserialization time, but this is definitely something you should observe later on. If you have a lot of data, you might want to split into smaller partitions, but here it's still acceptable from the time execution. I mean, you see also the process runs quite well. We can of course now go and generate 2 trillion, I think that's even more, trillion of rows. I will not execute this now to execute a job, but I will at least show that the number of partitions generated is actually the same. And we didn't talk about a topic how you can now influence the number of partitions. So the only influence factor which we have, unfortunately, with the data frame API on top, you don't have many flexibility anymore to really, at least for create data frame, to specify the partitions. But what we could do is restart one cluster in this case, and generate a cluster only with 3 workers. And let's just run our second generator function. And if we're gonna go now down here again, where we had the very huge data frame, we should see that the number of partitions is 3. And you can also see it in the number of parallelism, and also if you're gonna refresh the Spark UI under executors. So you see here we have the number of 3 cores. So, but I would like, because 4 is better for calculation, to go back to 4 cores. So start one last time our cluster and run the Spark partition and this function. So luckily the range function allows us to influence the number of partitions or data frame returns, and that's where we want in the last step to play around a little bit. So we are going now to generate, what do we have here? 2 million, no, wrong chapter. So 20 million data frames with 20 million rows. Let's start with 4 with 4 partitions. So we actually did it before just with 2 million. Now we do it with 4 million. So first of all, the important thing is we see that our number of partitions is again 4. And if you go to stages, we observe that we have 4 tasks executed. And if we go now into the details again, you see that we have here quite equivalent. Slight deviation can also be my non-very performant laptop, but as we have also some more data now, it needs also some deserialization time sometimes. So that's what you can see now. Now let's do the following. We can also say, okay, let's divide the data into more partitions. And of course, as mentioned, I would like to take a partition number which is dividable by the 4 cores which I have. And again, we see we have 4 partitions as expected. And if you go to stages, the second experiment, we can see that we have similar, a little bit longer running first round of tasks, and then we have a second task running here. And what we also can see, okay, again, it's still divided it into 2.5 million uniformly. Just the time, also the scheduler sometimes needs a little bit time to start executing the next task. Yeah, and so you can also see, okay, this executor or core here basically finish, and then the Spark scheduler started coordinating that this core is available and takes over the next partition to execute the task on it. And the last one is basically connected to the end, to the end of there. Now let's show what happens when I take like a partition size which is not dividable by or 4 cores in this case. So let's say, for instance, I want to execute this job only with 3 cores. If you go to stages, we gonna see in the third experiment, okay, just 3 cores are basically doing the job. I mean, we can do it. It's in this case not that much more inefficient, but you see, okay, if I have someone, a person, or in this case, a core which can do something, but just standing around does nothing, you're just wasting the available resources you have in your cluster. And you also see that the distribution happens here, of course, uniformly again, 20 million divided by 3 in this case. You can also play the same game the other way around. So we can say, okay, let's take a little bit higher number, that the number of class V cores which we have in this case. So let's take 6. And also the runtime is not significantly higher here, but or lower. But what you see here is we are running the 4 tasks, and then 2 cores are sitting around, and the other 2 cores have to execute additionally. And then here you can also see the total time across tasks. It's 8 seconds. Let's go for another experiment. Let's show now what happens if you go with a very huge number. So we take 200 partitions now, and I mean, this was not too bad. You saw it here in the execution time, but let's also observe this here. So you see it's still 3 seconds, but if you're going here to the Spark scheduler, you see that the total time across all tasks is 9 seconds. That's the most important thing. The other thing is only coordination of the driver node, basically. And you see it's like totally scattered. We have like a well, distributed number of records, but the duration time is like different. Sometimes you have some serialization, sometimes the scheduler needs to coordinate a little bit more, and it's gonna become even more serious if you suddenly go with 20,000. This would mean around 1,000, if I did miscalculated, rows. And you already see it here, it runs significantly longer. You can play the game until 2 millions, and that's basically also like on file size level, a similar thing which is happening when you have really small file sizes, which we can observe in one of the next episodes. So let's go to stages and have a look on the stage here. And now you see, okay, we have really long scheduler times. So the execution time is usually, here in this case not, but usually like one of the smallest part. And that means we don't use our resource efficiently. You see that, I mean, the values of execution time are that low per task that it doesn't show even up. Maximum is 45 milliseconds. Some other ones are really short. And you also see, okay, I calculate correctly 1,000 records, and you really have like a high distribution. We can also sort here based on the duration. I think I already did. So we start with 45 milliseconds, that's the highest, and if you go down, it's basically not even visible how much execution time we have. So what's our takeaway here is it's always important to not have the number of partitions too low, but also not too high. So you want to, like in size, you should say, okay, 100 to 200 megabytes. I think it's a good way to not overload the memory of your work. Is it also gonna need memory for other topics? You also avoid less garbage collection by that, and yeah, neither too high, neither too low, and by that you're gonna have a perfect execution. We're gonna deep dive into the stages in another episode a little bit deeper, but if you see that the green part is really small compared to your scheduler time, task visualization time, or even garbage collection time, something is wrong. And if you have like a scattered like that, like really with some more distribution, if you would have more data, we're gonna see way better statistics. Then you really have to have a look if you're only having narrow transformation, that already something really basic is not working well in your setup. And with that, thanks a lot for today's sessions. Thanks for listening. As always, feel free to comment below. Feel free to comment if you feel like I explained something differently and not the correct way as it should be. I'm also learning here, and of course follow my channel, and we see each other on the next episode. Thank you, and bye bye.